Hey guys, in this video I'm going to present a solution to USAMO 2018 problem 4. Firstly, we'll take a look at the problem statement. We are given a prime p and p integers a1 up to ap. We are asked to show that there exists an integer k such that the numbers a1 plus k, a2 plus k, and so on up to ap plus p times k produce at least p over 2 distinct remainders upon division by p. A reasonable first step is to fix any indices I and j and take a look under what conditions ai plus I times k and aj plus j times k produce the same or distinct remainders modulo p. So let I and j be indices from the set 1 up to p. And now let's just assume that ai plus I times k is congruent to aj plus jk modulo p. We want to rearrange this for k, so let's first bring all of the k terms to the right and the other ones to the left. We get that this is equivalent to ai minus aj is congruent to, well, j minus I times k modulo p. We know that any residue class modulo p that is not 0 has a multiplicative inverse. We would like to multiply by that so that we have an isolated k here, but of course that does not work if I is equal to j. But if we take a look at that case, then this congruence is always going to hold, so this is not an interesting case anyways. So let us also assume that I is not congruent to j modulo p, which is equivalent to I is not equal to j because they are between 1 and p. In that case, this is equivalent to k being congruent to ai minus aj multiplied by the multiplicative inverse of j minus ai, which we write as divided by j minus I modulo p. The big takeaway is that this congruence is true for exactly one residue class of k. So if we let k range from 1 up to p, for instance, then this congruence is going to hold exactly once. And I'm going to write this important fact down in orange right here. One model for visualizing that we have exactly one relationship between any distinct I and j in this set is to consider a complete graph G where the edges are colored with the numbers k equals to 1 up to p, where we color an edge I, j with k if and only if k is congruent to ai minus aj divided by j minus I modulo p. So let G be the graph on the vertex set V, which we want to be the set of positive integers less than or equal to p, so call this V. And then we want G to be the complete graph on that set, so this is V comma V over 2. I want to explain this notation briefly. So a graph is a pair of a vertex set and an edge set, where the vertex set is any set and the edge set is a subset of the set of two element subsets of V. And since we want to consider the complete graph, we actually have as a set of edges exactly all of the two element subsets of V. And we want to color any edge, so we color any edge I, j with the unique integer k in the set V again, but now as considered as a set of colors. So color the edge I, j with k in 1 up to p, such that ai plus ik is congruent to aj plus jk modulo p. And again, this works because we know that we can always find such a unique k in this set for I and j distinct. Since the number of edges in G is the cardinality of V over 2, which is the number of ways to choose two elements out of p elements, or p over 2, which is equal to p times p minus 1 over 2 edges. And we have p colors, namely the colors 1 up to p, we can conclude that if we take a color with the fewest number of edges, that we can find a color k star in 1 up to p, such that we have at most p times p minus 1 over 2 divided by p, which is equal to p minus 1/2 edges which are colored with k star. Now it is a good guess that our color k star is actually of the form that we want, because there are few edges colored with k star, so we might expect many different remainders upon division by p when substituting k star. Therefore, we only want to restrict ourselves to that color from now on. So let us define g star to be the graph v, e star, where, of course, we want this set, so the set of edges which are colored with k star, to be equal to e star. We notice that g star has only at most p minus 1 over 2 edges, which is very few in comparison to the number of vertices, namely p. Therefore, we can deduce a lower bound on the number of connected components of g star. So let c1 up to cl be the connected components of g star. We know that any connected graph on n vertices has at least n minus 1 edges, because a minimal connected graph on n vertices is a tree, and a tree on n vertices has exactly n minus 1 edges. Each of the connected components of g star induce a connected subgraph in g star. Furthermore, every edge of g star has its endpoints lying in the same connected components of g star. So we can use the just derived inequality on each of those components and sum it up to obtain a lower bound for the size of E star. Namely, we get the magnitude of E star is at least the sum of I going from 1 to L of the number of edges in the induced subgraph by Ci, which is at least the magnitude of Ci minus 1. Now, since every vertex lies in exactly one of those components, the sum is equal to the magnitude of V minus L. We already know the value of the magnitude of V and can bound the magnitude of E star from above by P minus 1 over 2. So let's write this down. Here we have a P minus L, and all of this is less than or equal to P minus 1 over 2. Rearranging for L yields L greater than or equal to P minus 1 over 2, or P plus 1 over 2. Lastly, we notice that if we take any I and j in different connected components of G star, then the edge I, j does not lie in the edge set E star, which by definition implies that AI plus IK star is not congruent to AJ plus JK star modulo P. So we can just take L different values from this set, namely one from each connected component, and from what we have here, this is going to produce L different remainders upon division by P, and therefore in total we also get at least, and in fact exactly, L different remainders upon division by P, which we have already bounded from below by P plus 1 over 2, and that is of course greater than or equal to P over 2, which is what we wanted to show, and therefore we are done.